I see. Okay. 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 And the chalks, these are all colored chalks. I think all are colored. No, I want the white chalk.
White on.
Okay. Pardon? Yellow chalk, yeah, but white chalk is better, I think. Let's get some white chalk. Thank you. If you want, you can move some of these chairs there. That will be easier. Let's move them. Right? No, you can keep it in. Yeah, I don't know. Is it visible from there? If it's too much in the corner, the board may not be visible. Maybe just I'll push it back. This also, I think, should push back. There is one chair here. Yeah, this is okay, and then there are some more chairs in case. Okay, I think I'll start. So this is going to be a course on general relativity. Which is a theory of gravity. Now, I'm assuming that all of you have say Newtonian gravity, right? From Newton's theory of gravity, right? So given that we have already a theory of gravity, right, that was written by Newton, right? So let me remind you, in Newton's law, in Newton's theory of gravity, if you have two masses m1 and m2, then the force is g m1 m2 by r squared, okay, and it's directed along the negative r hat direction, the radial direction. Okay, so that the force is attracted, right? This is the way we write the force in Newtonian gravity. So the first question is, I mean, what is wrong with this formula, right? Why do we need a new theory of gravity? And one reason that we don't want that this formula is not fully satisfactory, okay, is that it's inconsistent with special theory of relativity. Okay, this theory is not consistent with special theory of relativity. Okay. And this you can see by thinking of a simple situation. Okay. So remember, suppose that tomorrow the sun just blows up, okay, for some reason. Okay. So this event we are going to see 8 minutes later, right? Because light takes about 8 minutes to travel from the sun to the earth. Okay, so if the sun blows up, we'll see that event 8 minutes later. Okay. But if Newton's theory is valid, okay, then we will feel the gravitational force, the change in the gravitational force instantaneously, right? Because this says that if the sun blows up, right, that means one mass fragments into many masses, okay, then each of them will have their separate gravitational force, and so the force will change, and that will happen instantaneously. So if this is correct, then this would mean that the gravitational signal comes instantaneously, whereas the electromagnetic signal, right, comes after 8 minutes. Okay. And this is inconsistent with the general principle of special theory of relativity, which says that no signal can travel faster than light. Okay, if Newton's law was valid, we could, here are some chairs. There are some chairs here. In case you can move it also if you want. So if this is valid, then this will mean that gravitational signal will travel faster than light. Okay, and this is what we don't want in special theory of relativity, because the general principle is that every signal, okay, no signal can be transmitted faster than light. Now, of course, you can say that the special theory of relativity may not be valid for general relativity, right? And that you can say, okay, this will be a separate theory, right, which you have to use, and special theory relativity used for electromagnetic interactions. Okay, but it's not a fully satisfactory situation. But of course, the reason that we believe in general relativity is because there are experimental tests of general relativity. Okay, and we will see some of these tests. Okay, but this was one of the motivations why Einstein decided to look at the theory of gravity more carefully, right, to try to make it consistent with special relativity. And in general relativity, right, we can ask the same question: if the sun blows up tomorrow, right, how long will it take for us to feel the effect of gravitational force, the change in the gravitational force? And that will be exactly the same as the light travel, right, which is about 8 minutes. Okay, so in general theory of relativity, the signal will not be transmitted instantaneously, but only after 8 minutes. So this is the motivation for why we want to consider a new theory of gravity. Are there questions? Yes.
Why is the signal?
Well, that's not obvious, of course obvious. We'll see that it will happen, right? In general relativity, when you can calculate, ask the same question, right, and we'll see that the signal actually travels with the speed of light. Yeah, but it's certainly not obvious from what I have said, right? Because I have not even said what the general relativity is. Yes.
In case of electromagnetic physical force, it is not something per se physical property. Why should it be restricted?
Well, we'll see that in general relativity, it is the gravitational wave that carries the signal, right? So there also it is something that is physically propagated, right? The gravitational wave. So the physics will be exactly the same as in electromagnetism. Okay, but again, that's in Newton's theory, right? You will not have that feature, right? If something moves, it will immediately transmit the signal far away, right, without requiring any time. There will be no physics, nothing actually physically propagates from one point to another point, right? But clearly, if Newton's theory was right, then we could send signals, right, by faster than light, because we just take a mass here and move it, right, and that effect will be felt everywhere at the same time, right? So you can certainly send signal by moving a mass, right, and hoping that somebody else far away will detect that change in gravitational force because of the movement of the mass. Yes. Yes, the discovery of gravitational waves, for example, is a direct verification that gravitational waves propagate. Right? Gravitational waves have been discovered, right? Just the electromagnetic waves, right, can be detected. Gravitational waves can also be detected, right? And that clearly shows that the signal actually propagates by waves. Yes. Yes. Well, smaller scale, the point is because things move very fast, right? If you take two masses which are close by, right, the delay will be very little, right? And the Earth scale, okay. The gravitational waves are much bigger scale, right? Because the black holes, for example, which the gravitational wave that was first discovered, right, happened because of the merger of two black holes, which is billions of light years away. And you can estimate the time at that when that happened, right? And that effect we feel billions of light years later, right? And that's the one confirmation that gravitational wave does take time to reach us. Yes. Well, speed of gravitational waves, I don't think has been measured to that accuracy like that. Right? But roughly, by the fact that the gravitational signal that we see is coming from so many years ago, right, and so far away, that gives a rough estimate of what the gravitational wave propagation signal is. But certainly, the light is much easier to detect. So that's why the speed of light has been measured to a very, very good accuracy. Right? Certainly, gravitational waves are nowhere close to that. Any other question? Okay, but of course, the fact that gravity propagates with waves, we'll see only later, right? Right now, I have not said anything about general relativity. Okay? But it's a shortcoming of Newton's equation that the gravity doesn't propagate with waves, it just propagates instantaneously. Okay, so the tools that you have to use, okay, so let me just say the basic postulate of general relativity. Okay? And that postulate is that the gravitational field is a geometry of space-time. So because of this, okay, the first several lectures will devote to understand what you mean by geometry, right? It is not going to be the usual Euclidean geometry that you are familiar with, but the Riemannian geometry. Right? So that's what will constitute the first several lectures of this course. Okay, so we need to study Riemannian geometry. Okay, so let me then begin by giving the general introduction to Riemannian geometry, okay, and how it differs from Euclidean geometry. Okay. So in Euclidean geometry, let's suppose that we have 2 points which are close to each other. Okay, say let's say 3-dimensional space which we call x1, x2, x3, and this point is x1 plus dx1, x2. In this case, the minimum distance between these 2 points is obtained by just drawing a straight line between these 2 points. And distance, okay, which I'll denote by ds, is given by square root of dx1 square plus dx2 square plus dx3 square. Okay, just a simple coordinate geometry. Okay, this will be the distance between 2 neighboring points. Is this okay? So this we can generalize first to n dimensions, right? We don't have to restrict to 3-dimensional space, and n dimensions doesn't mean that you have to actually visualize what the n-dimensional space looks like, okay? But just think of describing it using coordinate geometry. Okay? That n-dimensional space means that to specify a point in that space, you need n coordinates. So in n-dimensional space, the formula will be ds square as dx1 square plus dx2 square. Okay. Now let me say what happens in the Riemannian geometry. Okay. So again, take 2 points which are close to each other. And the formula for this that we have written changes to ds square as sum over ij equal to 1 to n where these are some functions of x1 to xn. Okay, so distance between two neighboring points is not just the sum of squares, okay, square root of the sum of squares, but it's a more complicated formula, okay, where you have a function gij of x for every pair I and j multiplied by dxi times dxj, and that gives you the square of the distance. Shortest distance, yes, indeed. So you'll always talk for infinitesimally close points, you'll always talk about the shortest distance between these two points. Because of course, given two points, you can always draw a curve like this, right? That will have a different distance. Okay, so you are always talking about the shortest distance. Is this clear? The summation symbol is familiar to everybody. It basically means you have sum over I and j from 1 to n. Okay. So from this perspective, the Euclidean geometry is a special case. Special case. Where gij of x is delta ij. Okay, this is the Kronecker delta. Okay, is this symbol familiar to everybody? Is there somebody that is equal to 1 when I is equal to j, and if it's 0 if I is not equal to j. Okay. So if you take gij of x to be delta ij, then this reduces to what we had earlier, dx1 square plus dx2 square plus dxn square. Okay, so Euclidean geometry clearly is a special case of Riemannian geometry. Okay, but Riemannian geometry is more general. Okay, now let me introduce a convention which we'll be using, okay, which is called the summation convention. And this convention says that any index that appears twice is automatically summed over. From 1 to n. So in this convention, I'll write this formula. Okay, so this formula in this convention will be written as ds square as gij of x dxi dxj. Why? Because you see that I index appears once here and once here. Okay, it has appeared twice in the expression. Right? So it's automatically summed over. It's understood that I is to be summed from 1 to n. Similarly, j index appears once here and once there. So it's automatically understood that this is j is summed from 1 to n. So you don't have to write these summation symbols explicitly. Okay, so this is just a convention, just a way of rewriting the same thing. Okay. And it's useful because we'll get summation sums over indices in several places, as we'll see. Yes. We'll be following the same convention, but we'll always have indices. If the index is repeated, we'll see that if you do things correctly, right, you'll always have indices which only appear once below and once above. right? We will not encounter situations where the index appears twice but both below. Right? If it happens, then you explicitly say that you are not summing over. Right? Sometimes you may need, for some reason, an index that appears twice, right? But you don't want to sum over them. Then you explicitly say that there is no sum over this index. Okay, it's more economical to do it that way than writing summation symbol for every time you have a sum. Okay, but again, this is just a convention, right? There's nothing, no new physics in this. Are there other questions? Yes. What exactly? Well, this is what is called a metric. So Gij of x is called a metric. And this takes different values on different spaces, right? So different Riemannian different metric describes different geometric spaces, right? So it doesn't have a fixed value. We'll work out some examples later. Here there's a switch, I think, right? This one. Oh, remote, I see. Oh, okay. Okay, now I just said that different Riemannian spaces have different metric. What about if you have different metric? Are they different Riemannian spaces? Right? Suppose I give you two functions, Gij of x and another function, some g tilde ij of x. Okay. Do they describe different spaces? And the answer is that it's not always true that they describe different spaces, because some of these changes in the metric can be induced by change of coordinates. Okay. So let me explain what that means. So we have this formula, ds square is Gij of x, dxi dxj. Now suppose we choose new coordinates, which I call x prime 1 to x prime n, such that x1 is equal to some function f1 of x, x2 some function f2 of x. So this vector sign on top, okay, will basically mean the set of all coordinates x1 to x. Okay, so that's what it means by a function of this vector. Okay, it's a function of x1 to xn. Okay, and so on. Pardon? Sorry, yeah, prime somewhere. x1 is f1 of x prime. And we can also consider the reverse transformation. X prime 1 is, say, g, I will not use g, say phi 1 of x, x prime 2 is equal to phi 2 of x, and so on. Okay, and now we want to rewrite this distance square in this new coordinate system, x prime coordinate system, and that is not hard. Okay, so the same formula ds square I can now write as Gij of x As long as these are infinitesimal, dxi I can write as okay. So what have I done? This is just expressing a change of xi as in terms of change in the x primes. And this sum over this k is repeated so that the index is summed over. Right? So you're using in this formula the fact that dxi can be written, okay, that we are just changing variables. These are independent variables. X1 to xn is one set of independent variables. X1 prime to xn prime is another set of independent variables. So dxi can be written as okay. Let me write the sum anyway. Right, because xi after all is a function of x1 prime to x2 prime, x1 prime to xn prime, right? So if you want to find how much this function changes, if you make an arbitrary change in x1 prime to xn prime, right, we'll calculate the derivative of this function with respect to each x prime and multiply by the corresponding change in the x prime. Right? That's what this formula is telling us. Is this clear? So this one I can write as g prime kl x prime times dx prime k dx prime l, where g prime kl of x prime by definition is whatever multiplies this thing, which is gij of x prime del xi del x prime k gij of x. Thank you. Is this clear? Okay. And we can make it look like the original formula by simply changing the names of the labels, right? Because the k is summed over, L is summed over anyway. So you can write this as g prime ij of x prime dx prime I dx prime j. So what this tells us is that suppose you are given two matrices. One is gij, the other one is g prime ij. They look different, but they don't necessarily describe different spaces or different manifolds, because there may be a coordinate change from x to x prime that actually relates the two matrices, okay, in this form. So here g prime ij and gij actually describe the same space written in different coordinate system. Is this clear? Okay. So I'll give an example. Yes.
So are there any constraints on the set of functions there?
Well, we are assuming here that at least in a small region they are invertible. Right? You can write x in terms of x prime and x prime in terms of x. Right? In some places there may be singularities that there may not be one-to-one map, where you have to be more careful. Right? So right now you are assuming that at least in the region that you are working in, region of space, this relation can be inverted.
Singularities may be of the functions.
Yes, they can be of the functions, exactly.
Then at that point, the transformation will not be valid, or be careful about.
You have to be careful about. Yeah, exactly.
They don't say anything about the nature of the original
Space, no, not necessarily. Right? It could be simply that it's because of the change of coordinates. Okay, and we will see some examples.
So this locally this phi is f inverse.
Yes, phi is f inverse. F inverse in a functional sense. Exactly. Okay. So I'll start with an example that is probably familiar to most of you, which is the polar coordinates in 3 dimensions. Polar coordinates in 3D. Okay. So you had introduced this x1, x2, x3, right? In 3 dimensions, these 3 coordinates, x, y, z, right? Which is normally called x, y, z. Okay. Now let's change coordinate system to polar coordinates. Okay. So how do you do that? You introduce r theta phi, such that x1 is r, x3, let's start with x3, r cos theta, x1 is r sin theta cos phi, and x2 is r sin theta sin phi. Okay, so this is how you introduce polar coordinates. And now we can follow this kind of procedure to express the Euclidean metric, right? dx1 square plus dx2 square plus dx3 square in this polar coordinate system. Okay. So I'll just write down one example. So dx3, for example, will be cos theta times dr minus r sin theta d theta. Right, because dr times cos theta and then cos theta times, sorry, r times minus sin theta d theta. Okay, that's what I've written there. Similarly, dx1 will have a little more complicated term. Let me write that also. So this will be sin theta cos phi dr. Then there will be plus r cos theta cos phi d theta minus r sin theta sin phi d phi. And it's basically an application of this formula that you are using. Okay? Write dx1, dx2, dx3 in this way. Okay. And I'll leave it as an exercise to check that ds square, which is dx1 square plus dx2 square plus dx3 square, can be written as dr square plus r square d theta square okay. So this means that the Euclidean metric is the same as this metric, right? If somebody gave you this metric, right, it's the same as Euclidean metric. Okay. And furthermore, the names don't matter. Okay, so if somebody gave you a metric like this, it is still the Euclidean metric, right? Because all I have done is that I have called r as x1, theta as x2, and phi as x3. Yes, so that you have to specify, right? But locally, right, the range doesn't matter. Locally, it's just Euclidean metric. Okay, this range will start coming into play only when you look at the global structure of the space. Is this clear?
This found the metric of the same coordinates.
this form. Okay, when I give you this, I don't tell you what coordinate system I am using, right? I've just given you some coordinate system x1, x2, x3 in which I have specified the metric, right? And then some coordinate system x1, x2, x3 I have specified this metric, right? These two metrics are the same. That's the claim. These two metrics describe the same space, right? You can relabel them, right, as something else, r theta phi or x1 prime, x2 prime, x2 prime. But the point is that there is a change of coordinate, right, that relates these coordinates to these coordinates, which give you back that metric.
Any pair of matrices where such a transformation exists will always be equivalent.
Exactly, right? So that when you suppose you are given two matrices, ds square, okay, as one set of functions of gijx, another set of functions of gijx, right? So what will you do to test if they are the same, right? You first change one of the coordinate labels from x to x prime. Gijx and gijx prime, right, is the same metric, right? Because just coordinate name doesn't matter. Okay? Then you try to find if there is a transformation of this kind, x to x prime, okay, that takes gijx to that g prime ij of x prime.
No, but just giving these two metrics,
Yes.
we can't say that whether the spaces are same, right? Because I mean, it should be that the distance between 2 points, whether you compute from this metric or that metric, that should be
Exactly.
So you have to also give the transformation rule between this x1 and this x1.
No, so okay, the coordinates are up to you to choose.
Right.
So I cannot tell the distance between 2 points will be the same because you might have chosen the wrong points, right? So the statement that two metrics are equivalent is that if it is possible to find a change of coordinate, okay, so that the distance between 2 points are the same in these two metrics, then they are the same metric. Okay. So the fact that the fact that you are allowed to make a change of coordinates, right? That is part of the definition of what different Riemannian metrics are. Okay. So that allowance you always have to give, right? Suppose if I give you dx1 square plus dx2 square plus dx3 square and dr square plus r square d theta square plus r square sine square theta d phi square. I don't tell you what change of coordinate you have to make, right? If you can make any change of coordinate that relates these two, then they are the same metrics.
Take the functional form of one metric, one set of functions.
Exactly. The functional form you should be able to change, right, by a coordinate transformation, right? The fact that you call the new coordinates r theta phi or x1, x2, x3 makes no difference, right? As long as you can find a transformation that makes the original function into a new function, they describe the same space.
Is there any systematic way to find that?
We'll see. We'll. I mean, this is one of the questions you have asked, right? That given two metrics, how do you know they are the same, right? There are infinite number of possible ways to make coordinate transformation, right? I mean, you cannot possibly go through all the infinite number of possible ways, right, to check if the two metrics are the same, right? So this is one of the central questions that we'll ask in the first part of the lecture, right? How do you decide if the two metrics are the same or not?
So you are saying that there can be multiple coordinate transformations relating to
That is, yes, some in spatial cases there can be, but that's not what I'm saying, right? Okay, that is true in some cases, but what I said is not that. What I said is that suppose you are given two functions, okay, two set of functions, gij of x and g prime ij of x. We want to know if these two describe the same space, right? The way I have presented it here, you have to find a coordinate transformation that takes one to the other. Okay? If you have found a coordinate transformation, then of course they are the same. Suppose you are not able to find it, right? Then how do you decide if they are the same or not, right? You cannot possibly test all the infinite number of coordinate changes and test this, right? So that's what you have to try to understand, that how possibly we could decide if the two metrics are the same or not. Yes.
Essentially, we have different statistics here.
Yes, that's right. That you should be able to find a coordinate transformation when that takes one to the other.
Essentially, the same across what we measure is same across coordinates.
Exactly. After making an appropriate coordinate change. Okay. Yeah, well, Euclidean is a special case of Riemannian geometry, but yeah, you cannot say whether it's Euclidean or not. Yeah, it is not looking like that, but if you can make a coordinate transformation where it does look like that, right? So if you can make a coordinate transformation which makes it look like this, then it's Euclidean geometry, right? Even if the metric is not delta ij, right? Because the statement there is that in Euclidean geometry the metric is delta ij, but doesn't mean that if the metric is not delta ij, it is not Euclidean, right? It is possible to make sometimes it is possible to make a coordinate transformation that takes you to delta ij. So you'll call a geometry Euclidean if there is any choice of coordinate system in which the metric looks like delta ij. Exactly. Okay. So from this perspective, right, it is, I mean, to show that two metrics are the same, right, that requires a finite number of operations. If you have just found a function, found a set of coordinate transformation that takes one metric to the other, you are done. Okay. On the other hand, to show that the two metrics are not the same, right, that looks like it requires infinite number of operations, right, because you have to choose one function after another and check if one metric goes to the other, right. So the second problem is what we will try to address, right, how you can possibly decide if two metrics are not the same by a finite number of operations. Okay, so let me now give another example which is a little non-trivial. And that example will be the surface of a two-dimensional sphere. Okay. So a two-dimensional sphere we normally describe as x1 squared plus x2 squared plus x3 squared equal to some constant. Let's call this a squared. Okay, a is some constant. Right? This is the way we describe the surface of a two-dimensional sphere. It's clear? Okay. What we want to do is to write down the intrinsic metric on the surface of a two-dimensional sphere, okay, which basically means that suppose we have 2 points close by points on the sphere. How to describe the distance between those 2 points? Okay. And because the sphere is two-dimensional, okay, you should have only 2 coordinates, not 3. Right? To specify a point on the surface of a sphere, you need only 2 coordinates. Right? Here, for example, if we are given x1 and x2, x3 is given. Right? x3 is fixed. It's not an independent coordinate anymore. Right? So this is the sense that the surface of a sphere is two-dimensional, not three-dimensional. Right? Because you only need 2 coordinates to specify the point on the surface of the sphere. Okay? So it is not good enough to write a metric like dx1 squared plus dx2 squared plus dx3 squared. Okay? Because we shouldn't have 3 independent dx's, right? You should have only 2 independent dx's. Okay? So first, let me give the brute force way of describing surface of the metric on the surface of the sphere, okay, which is valid locally but not everywhere. But in that example, I should have said that this change to polar coordinate the r equal to 0 point, okay, the map is singular. It's not one-to-one, because imagine that in the polar coordinate, you take the point r equal to 0 and two values of theta and phi, right? In the Cartesian coordinate, they correspond to the same point, x1, x2, x3 equal to 0, right? So that's the reason why the map is not one-to-one, right? The origin, for example, right, doesn't have a unique r and r, theta and phi. Right? It has r equal to 0, but theta and phi are completely arbitrary. Okay? So that's an example of the case where the map can become singular. Okay, and that is also reflected in the way the metric is. I think it's now hidden. Okay? If you remember, the metric had a dr squared, then there's an r squared d theta squared, right? And r squared sine squared theta d phi squared. So if r is 0, right, that means that if the 2 points are separated by some theta separation, then there is no distance. Right? That's a signal that something is wrong. Right? It may happen that the metric itself is singular. Right? That there is no change of coordinates by which you can repair that. Okay? Or it can happen because the coordinate transformation is singular. Okay? In this case, we know that it's because of the coordinate transformation, because clearly in the Cartesian coordinate system, you don't have any such problem. Right? As long as the separation is non-zero, right, the distance is non-zero. Okay, so the brute force way of getting the metric is to just eliminate x3. Okay, once you have this, then x3 is plus or minus square root of a square minus x1 square minus x3 square. Okay. So you use x1 and x2 as our independent coordinate system. Okay. This is not a one-to-one map because there are two values of x3, right, which corresponds to x1 and x2. So there are 2 points on the sphere. Right? You can visualize what's happening, right? If you have a sphere, if you specify the point in the x1, x2 plane, right, that has 2 possible values, right? There are 2 points, okay, which are separated by vertical distance, which correspond to the same value of x1 and x2. So specifying x1 and x2 doesn't specify the point uniquely, but let's suppose that you are in the northern hemisphere, right? Just locally, suppose you are in the northern hemisphere, then it's fine. Then we just pick the positive side. Pardon? Sorry, x2 square. Thank you. So then dx3 will be given by x1 dx1 plus x2 dx2. I think there's a minus sign also. If we choose the plus sign, we have to do minus plus, and then square root a square minus x1 square minus x2 square. Okay. And that's substitute here. So ds square will become dx1 square plus dx2 square plus 1 over a square minus x1 square minus x2 square times x1 Is this clear? Okay. And now you can just combine things, put the calculate the coefficient of dx1 square by adding this term to this term, right? Calculate the coefficient of dx2 square by adding this term to this term, and then there is a dx1 dx2 cross term. So that's part of the matrix. So the three independent components, g11, g22, and g12, you can read out from here. I should have said that gij can be always taken to be symmetric, right? Because there is sum over I and j, right? Gij dxi dxj, because dxi dxj product is symmetric. Any antisymmetric part of gij is just gone, right? So we'll always take Gij to be symmetric. Okay, so this is one way of getting the metric. Why? Because if the way we have introduced Gij, right? We have written ds square is Gij of x, dxi dxj, right? Okay. So this product is always symmetric. Right? So any antisymmetric part of Gij is not going to affect ds square. So that's why you can always take Gij. We'll always take Gij to be symmetric. Yes. Yes, indeed. We'll always take Gij to be symmetric. In Riemannian geometry, Gij is symmetric. Right? So far, what I have done, right? It makes no difference if we add an antisymmetric part of Gij because it just drops out anyway. But subsequent formula that we'll be using will write assuming Gij is symmetric. Right? Otherwise, it's only the symmetric part of Gij that will enter all formula. Right? You have to explicitly write Gij plus Gji. Right? Instead of doing that, we just assume that Gij is symmetric because the metric doesn't get affected by Gij anyway. That's antisymmetric part anyway. Okay, once you have said that the only content of Gij is specifying the distance, right? It is clear that the antisymmetric part has no role to play. Right? All subsequent formula will be this will be the starting point for all subsequent formula. Right? So if the initial formula didn't depend on the antisymmetric part of Gij, then obviously no other formula can depend on the antisymmetric part of Gij. Right? Because this is the only way Gij is going to enter the description of the space. Is this clear? Okay, so the other way is to use the form of the Euclidean metric in polar coordinates and then do the same thing. So we had this formula ds square is dr square plus r square d theta square plus r square sine square theta d phi square, right? Is polar coordinate. And in the polar coordinate, the equation of the sphere is just r equal to a. Okay, so just substitute that here, right? So if you set r equal to a, then obviously dr is 0. Right? 2 points on the sphere. There's no change in r, right? By definition. So ds square will be given by a square d theta square plus sine square theta d phi square. Is clear? Because dr is 0, right? If r is equal to a. So these two metrics better be the same, right? Because you are describing the same two-dimensional sphere, right, in different coordinate system, x1, x2 coordinate system and theta phi coordinate system. Okay. So it's a simple exercise. Okay, it in fact follows from what you have already done. Okay. Find the coordinate transformation from x1, x2 to theta phi that takes one metric to the other. Okay, it will basically be restriction of whatever we had written in the changing from Cartesian to polar coordinates. Is it clear what we are supposed to do? Right? We have to find x1 as a function of theta and phi, and x2 as a function of theta and phi. Those functions you have to find, okay, such that this metric over here becomes this metric. Okay, you see in particular that here a appears as an overall factor, Here it looks a little more complicated because A is not an overall factor. Right? A is somewhere else. But nevertheless, the coordinate transformation will take care of it. So this metric, this one or this one, which are the same, is non-Euclidean. Which means that it's impossible to find a coordinate transformation that will make this into dx square plus dy square. Do you believe it? How does one? Yeah, that's the question, right? I mean, intuitively you can say that okay, surface of a sphere is not the same as a plane, right? But how do you prove it? Right? Here you have two metrics. One is here, right? The other one is dx1 square plus dx2 square. Right? How do you know that it's impossible to find a coordinate transformation that takes you from here to dx1 square plus dx2 square?
It should be valid on the full surface of the sphere.
Even locally.
But locally, you can
Well, locally means infinitesimally, right? Here, what I mean locally is that you have to find a certain finite region where it will look like a flat metric. Right? That is not possible. Well, that requires that that assumes that you are using x1, x2 as coordinate system, right? But I'm not telling you that in this coordinate system it should look like dx1 square plus dx2 square, right? I say, okay, I will find another coordinate system, y1, y2, which is has complicated relation with x1, x2, and with theta phi, in which the metric will look like dy1 square plus dy2 square, right? I mean, if you believe that this is not Euclidean, you have to refute that argument, right? How do you show that it is impossible to find such a coordinate system?
Maybe we can assume the form and then we will run it.
Yes, we can assume the form, right? But assume meaning you have to find a general form. We cannot assume any particular form, right? If you assume a particular form and run into a contradiction, that doesn't help, right? You have to say a general form, right? Y1 is some function of theta phi, y2 is some function of theta phi, and then so that there is a contradiction. Exactly, some inconsistent PD you will get, right? That's basically what you have to do, right? But we'll see a systematic way of analyzing this question. Okay? And the systematic procedure will be the following, right? We'll try to construct out of the metric and its derivative some quantity that we'll argue is unchanged under coordinate transformation. Okay, imagine that suppose you can find such a quantity, right, out of metric and its derivative. That doesn't change under coordinate transformation. Then we can evaluate this on this metric and on flat space, Euclidean metric. And if they have the different values, then you know that it's impossible to find a coordinate transformation that takes one to the other, right? Because that quantity doesn't change under coordinate transformation. Is this logic clear? So we have to identify such quantities which do not change under coordinate transformation. If you can find such quantities, then you can use those to test if two metrics are the same or not.
Can we have same help for those quantities for
Then you find something else, right? So this is, so I said that the other way, right, to show that the two metrics are equivalent. It's a finite problem because you have to just find a coordinate transformation, then you stop, right? Reverse was not a finite problem, right? Here the reverse will be a finite problem because you can identify such quantities, because for any one of the quantities, if you can show the two things are different, then you know that it's not possible to find a coordinate transformation, right? You don't have to keep checking again and again. Okay, so certainly a single quantity is not going to do that, although in 2 dimensions indeed locally a single quantity does the job, but when you go to higher dimensions you need more quantities, right? A single invariant is not going to help you always. Yes.
ds squared itself?
ds square, but this ds square is not really a number, right? ds square is invariant, you are right? But it's not really a number. I mean, what do you do with the ds square, right?
You need to find a local.
Exactly, right? Some invariant at some point x. Right? And if that quantity, suppose you say that it's a constant on it as a function of x. Right? You calculate another invariant, right, which is another constant as a function of x. And they are not the same. Right? That can help you resolve this problem. Yes.
So you just mentioned that for higher dimensions you need more and more invariants.
Yes.
Does it mean that the invariants you're searching for are not scalar invariants?
No, scalar invariants, but there may be more scalars. One scalar may not do the job. Okay, sometimes it is also possible, is also there are cases where the scalar invariants are not enough. You have to do more work. Okay, but I think it will become clearer as we go along, right? What kind of invariants you are talking about. Right now, yeah, right now let's just look at finite matches, right? How rare are they? They are quite rare. I mean, they are set of measure 0 among the space of all possible metrics. Right? So in that sense, they are rare, right? You have to satisfy a very special condition to be able to make the metric into dx1 square plus dx2 square. Right? If you take even in 2 dimensions, if you take a generic metric, right, choose your favorite function gi of x, right? It's 100% of the time, right? 100 minus n that set of measure 0% of the time. You will find that that is not that cannot be transformed into dx1 square plus dx2 square.
Sir, we are looking for a invariant point. Such that for every geometry it is something.
Say yes, something like that. Yeah. Yeah. Okay. I mean, in that process, we'll also discover more general quantities which are useful. Right? But this is the first thing we can try to look, right? To be able to decide whether a given space is flat or not, is Euclidean or not. Right? You have to look for something which it's easiest if it vanishes for Euclidean and doesn't vanish for the other one, right? For the one that you are looking for. Then, of course, you are sure that it's not Euclidean.
Then again, why, like any surface that we are considering, locally it is same as some R. Right? Then why is it not?
No, look, that's a coordinate. That's a question of topology, right? We are talking about, but you are talking about geometry. You see, a sphere, right? It's the same statement that the surface of a sphere, right, cannot be stretched to make it a plane. Okay, without stretching, you don't want to stretch it because stretching means you are changing the concept of distance, right? But if you don't stretch, right, a curved space cannot be made flat. Okay? Right? So that's the statement that this two matrix cannot be transformed by coordinate transformation. If you stretch, right, that's like you are changing the matrix, right? Because the distance between 2 points are changing, right, under stretching. Yes. Which requires 2 coordinates to specify a point on it, right? So a 2-dimensional space is something that requires where a point is specified by specifying 2 coordinates. Right? That's the sense in which it's 2-dimensional, because even though we started by saying that there are 3 coordinates, right? There's one constant among those 3 coordinates. So once you fix 2, the other one gets fixed.
Both of these coordinates are singular at some point, right? The ds square value.
Yes, indeed.
So is there any coordinates where you can, which is like valid everywhere?
No, in 2 dimensions, on the sphere you cannot do it. There's a coordinate system which is valid everywhere, but it's not necessary, right? You can describe different coordinate system in different regions, as long as you know what change of coordinate you have to do to go from one to the other. But geometrically, it may not be same as R2, right? Even just flat space, right? You can stretch it and make it crumpled in a sort of finite region, right? So topology doesn't change, but geometry changes. Okay, so once to distinguish between this topology and geometry, right? The fact that the 2D sphere is topologically equivalent to a 2D plane locally doesn't mean that geometrically it's the same. Right? So here you are talking about this finite structure which is geometry. I mean, another way of saying that topology only tells us when 2 points are close by. Geometry tells us how close they are, right? What is the distance? Right? So geometry clearly has more information than just topology of the space.
Two surfaces are to be geometrically same. It establishes the matrix over the topology.
But the metrics are same. I mean, to specify the metric, we specify the coordinate system, right? And then the point is the matrix will be the same under a change of coordinates, right? So that's what you are after, right? That how do we decide if the two metrics are the same? Right? So there is a change of coordinate that can make the two the same. Okay, so now we have to introduce some notions, some definitions. So metric was a two-index object, right? Okay. So now we are going to introduce the notion of general tensors. Okay. So let's suppose a I1 to IQ x is constructed from Gij and its derivatives such that under change of coordinates so here again all these indices are summed over. I1 to IQ are fixed, but J1, J2 up to JQ are summed over, right? Because they are repeated. J1 appears here and here, J2 appears here and here, and so on. Okay. So let's imagine that you have found some combination, something made out of metric and its derivatives, such that when you change coordinates, right, you already know what the change of coordinate, how the metric changes, right? So if things are made of metric and its derivative, you can find out how it changes when you look at the new metric. Look at the new metric. If the change is such that this relation holds, okay, then we'll call this a rank Q covariant vector, covariant tensor. Okay. So in this case, this a I1 to IQ of x is called a rank Q covariant tensor. So the example, let me give some examples. Gij, Gi1, I2 X is a rank 2 covariant tensor. Right, we had found the transformation law of G. Right, if you go back there, you'll see that it satisfies this condition. G prime I1, I2 of X prime is given by this with G I1, I2, J1, J2 of X. The second one, okay, is again straightforward, but it requires a little more thought. G I1, I2 of X, G I3, I4 of X is a rank 4 covariant tensor. Okay, what does it mean? Right? When I say this is a rank 4 covariant tensor, right? You evaluate this in the new coordinate system. So this means, so that the meaning should be clear. Right? So this means that G prime I1, I2 of X prime, G prime I3, I4 of X prime should be given by del that this is what this means, because A prime I1 to IQ X prime is that you take the same formula except that you replace everything by prime. Okay, this is prime. And similarly, on this side, A J1 to JQX is just G J1 J2 of X, G J3 J4 of X. Okay, that's the definition. So this, so you have to prove that this is a rank 4 covariant tensor, you have to check that this is true. Okay, and this is indeed true because individually this satisfies this times this, and this is given by this times this. And its derivatives. Yes, rank 2 covariant tensor, exactly. Right? But you can consider others, right? This one, for example, is a rank 4 covariant tensor. Not everything that is constructed out of covariant tensor is covariant. Right? Derivative of Gij, for example, we will see is not covariant. Right? If we just use Gij, yes, yes. No. Suppose this is true. It is not true for all cases, right? If this is true, then we will call this a rank Q covariant tensor, right? But there are certainly examples of cases where you can construct some multi-index object out of Gij and its derivatives, which is not a tensor, right? I mean, the simple example is that this quantity is not a tensor. Okay, this we'll see next time, I think. Okay, this still has 3 index, right? I1, I2, I3. But this you can show is not a tensor. Right? It doesn't have this property. So if you construct something out of Gij and its derivatives, which has this property, then we'll call this a rank Q covariant tensor.
It should be necessarily constructed from GIG only. There is no other way.
We'll see later that we extend this notion. We can extend this notion to include other things. But right now, let's just focus on GIG and these derivatives, right? Because so far the only data we have, right, is a metric on the space, right? So everything that all physical quantities have to be constructed out of that one, right? Later on, we'll introduce other fields like electromagnetic field, etc., and then we'll see that you can extend this notion of tensors to those cases. Right now, let's just look at the metric. Not necessarily. If it is antisymmetric, it has to be lesser than a dimension of the space. On two-dimensional sphere, for example, you can construct a rank force tensor, right? The indices will be repeated. It's not necessary that these two have to be all four different indices. Right? So it's not limited by the dimension of the space. But for antisymmetric tensors, you are right that if the tensor is fully antisymmetric in its indices, then of course you cannot have more than the dimension of the space. Is this okay? Because antisymmetric means if two indices are equal, then it vanishes, right? Okay, so all indices have to be different to get a non-zero value, right? And if all the indices are different, if each index takes n values, right, you cannot get more than n index. Okay. Okay, so next I'll introduce the notion of contravariant tensor. Okay, and the contravariant tensors are written with their indices up. So if a I1 to I u of x is called a contravariant tensor, okay, if the following holds. Is this clear? Yeah, the difference between this and the covariant tensor was that for the covariant tensor, it was a derivative of x with respect to x prime, right? For contravariant, it's a derivative of x prime with respect to x, that is apparent. So have we seen examples of contravariant tensor so far? GIJ was a covariant tensor, right? Pardon? See, dx is not a tensor. It's not really a function that way, right? Dx is the index up, but it's not a function. Pardon? X is also not a, x doesn't transform this way, right? X goes to f of x, right? That's a very complicated transformation. Okay. So the following statement is true. It's not completely obvious, right? But this is something you can prove. Okay. So regard G as a matrix. So regard G as n by n matrix. Okay. Then G inverse is the matrix inverse of G. Once you think of it as an n by n matrix, you can invert it, right? Pardon? Non-zero determinant. As long as at a generic point you will have non-zero determinant and you can invert it, right? For example, if we the sphere metric, right? If its dA squared is dr, sorry, it was a squared times d theta squared plus sine squared theta d phi squared, right? So as a matrix, G is a square and a square sine squared theta. The diagonal matrix, these are zero because there are no theta phi component. So G inverse will be 1 over a square okay, so this is what we mean by matrix inverse, right? Take the matrix inverse of G. Then define Gij as the ij component of G inverse. So in this notation, okay, once G inverse has been given, we have G theta theta as 1 over a square, G theta phi is 0, and G phi phi is 1 over a square sine square theta. Is this clear? Yes.
So G upper ij, x lower I lower dx lower j. Does it have any physical meaning?
Well, you have not introduced dx lower I dx lower j, right? And we'll never talk about dx lower I and dx lower j. Right? So dx will coordinates by definition will always carry upper index, right? And you are not going to raise and lower the index of coordinate. Okay, but Gij has other physical meaning, but not something like G upper ij dx lower I dx lower j. Okay. So now I'll leave it an exercise. This is a little more complicated exercise. And once you have proved this, then of course it's also automatic. Let me write the I1, I2. The G I1, I2 of x, G I3, I4 of x is rank 4 quantified tensor, etc. Is this statement clear? Okay, what you have to prove is clear. See, once this is proved, this is automatic, right? Because that just follows from the definition. Now this I leave for you to prove, but let me just give a hint of how you go about proving this, right? So for that you have to basically start with the transformation of the metric, which you know, which is given to you, right? Which was the starting part. So G prime Ij of x is this, right? Okay. This you can write in the matrix notation as G prime equal to A transpose G A, where A Lj, okay, let me write both. What is del is this clear? Right? You can see that this is the Lj component. Okay. So GKL ALJ, and here it's not quite in a matrix product form, right? But once you transpose it, right? So this is the Ki component of A, okay? But to write this as a matrix, right? The K should have been a column index, right? So A transpose Ik, right? A Ki is the same as A transpose Ik. Okay? So that's the sense in which G prime can be written in this form. Okay, this you have to just work out carefully. And once you have written it in this form, then G prime inverse is A inverse G inverse A transpose inverse. Okay. Using this, now you have to relate A inverse, okay, to these kinds of derivatives, which you can do, right? Where prime appears on top and this appears on the bottom. Okay. And using that, we should be able to prove this, that G is a rank 2 covariant contravariant. Okay. So of all the exercises I have given today, this is the one which requires a little more work and a little more thought. Okay, but please try to do this, okay, because this is going to be important and we are going to use this G upper Ij many times in our analysis. Okay. So I think today I'll stop here, right? And we'll continue this discussion of tensors tomorrow. Okay. And eventually our goal will be to find something that doesn't transform, like a scalar. Right? A scalar is a rank 0 covariant tensor or rank 0 contravariant tensor. Doesn't make a difference. It has no index. Right? If we find a scalar, it doesn't transform. Right? And then that scalar we can use to try to test if the two spaces are the same or not. Right? If the scalar has different values on different spaces, then we can be sure that they are not the same. The spaces are not the same.
At least one scalar which you can ensure the advanced spaces.
Exactly.
There can be various possibility that some scalars
Are the same, but at least as long as you can find one scalar which is different, then you are sure that they are the spaces are not the same.
Scalars can be function of x, right? Function of the points of the.
Yes. Then you have to make sure that by transformation, you cannot make one function to another function. Right? That's a much easier thing to test than tensors, right? Because here you have this matrices multiplying it. Right? In particular, if you find that the scalar is not a function of the points, right? Suppose you find a space where the scalar is not a function of the points, then clearly just the values being different is good enough. Yes.
So you said that derivative of Gij is not a tensor. So is this like a general statement?
In general, no. We'll see. We'll see later that it is possible to combine the derivative with something else to make it into a tensor. But just if you take derivative of a tensor, it will not be a tensor, right? And you can probably see also why, right? Because G prime Ij of x prime is So if you take a derivative of this, right, then the derivative can act on this, but that you can convert by chain rule into derivative with respect to x coordinate, right? That part is the what you need for it to transform as a tensor. But the derivative is also going to act on this, right? And those are the extra terms that spoil the tensorial property. Right? That's the reason derivative of a tensor is not a tensor in general. Okay, so we'll continue tomorrow. Yeah, go ahead. Okay.
Where you are motivating by GR.
Okay.
So in special relativity also we have a relativistic form of kinematics law.
Yes.
Newton's equation. So did people try that to like amend?
Yeah, in a sense,
Newtonian
that's how Einstein reached that, right? To amend Newtonian gravity, but it requires a big amendment, right?
No, so what I am asking is, so in special relativity, we are taught how Newton's law, second law in mechanics, is generalized.
Yes.
So did people try that way of making?
See, that
Newtonian
will
gravity
change the
relativistic?
particle motion,
Particle motion.
right? But not how fast the signal, the gravitational signal is
Yes,
traveling.
my question is, did people try to modify the force law also?
Well, that's what Einstein did, right? They found is that eventually you need this geometric formulation. Right? So, modification of the force of Newton. How they
I can see.